It's my pleasure to introduce Primoz Skraba from Josef Stefan Institute, who today will be speaking on an approximate nerve theorem. Thanks, Primoz.
Thank you, Henry, and thank you for fitting me into the schedule. So this is some work that I did with a student of mine, Dan Goetz, roughly maybe about a year and a half ago. I don't know if it's kind of as widespread as it should be, which is why I wanted to talk about it here. So roughly speaking, I think everyone who's listening to this or watching something like this will be familiar with the TDA pipeline, how we do topological data analysis, right? We usually think of some underlying topological space that we have some sample of, and then somehow we build a simplicial complex. It doesn't have to be simplicial, but we build some complex, and then we compute invariance. Not surprisingly, here today I'm going to be talking about persistent homology. So today what I'm going to concentrate on is this step and how we go from point samples to a filtered complex. This is usually the hard part in any, let's say, approximation theorem. So this is really what we're going to talk about today. So I think most TDA papers, if not all TDA papers, use the Nerve Theorem, the classical Nerve Theorem, either explicitly or implicitly. So just in case someone doesn't know what the Nerve Theorem is, what it is it says that, say that I have an open cover, and I'll define this in a second, of some suitably nice topological space, such that all non-empty intersections of these cover elements are contractible. What this says, if this condition holds, then the nerve of the cover is homotopy equivalent to the underlying space. So what that means is that we haven't lost any topological information. So now let's actually deconstruct this into some definitions. And again, I think most of you will know these definitions and seen them before, but just for completeness, what is a cover? Well, a cover is just a collection of sets that if we take the union of, we get the entire space, right? It has to cover the space. And what a good cover is, which what the Nerve Theorem actually talks about, is it says that for any finite subset of these of the cover, all these finite intersections have to be contractible. So let's take a look at what this would look like, right? So here we have our topological space, and we cover it with little sets, right? So here all the sets are roughly round, and so each of these little pieces has to be contractible, but also all intersections have to be contractible, and all three-way intersections, actually all higher intersections have to be contractible as well. And it's sufficient that we only consider finite things because in general, our space is nice enough so we don't really have any problems with, infinite intersections. And actually everything I'm going to talk about today, we're generally going to just assume finiteness pretty much everywhere, although I will highlight wherever things are perhaps can be extended to infinite, into infinite cases. One important thing is, since we're going to be talking about persistent homology, I don't really want to say contractible. I want to say topologically looks like a point. And I want to be kind of intentionally vague on this because there's a lot of different instances of the Nerve Theorem. And the condition that we require generally depends on what kind of statement we want at the end. So here, what I'm going to mean by topologically a point, I wanted to have the homology of a point, which of course is a much weaker condition than contractible. So first I thought I would give the example of kind of the case of the Nerve Theorem that I think everyone here knows, which is the check complex, right? So we have our points, we put disks or balls around the point of radius r, and we can take the union of balls as a topological space. And the check complex is essentially just the nerve of this, of these union of balls. So if we're in Euclidean space, because balls and intersection of balls are all convex, they're immediately contractible, which means that the nerve of the check complex, right? So the check complex, or the nerve of the union of balls rather, is automatically, they have the same homotopy type, right? But in most cases, we're not really this lucky. We don't necessarily care about the topology or the homology of a union of balls, but rather we use this as a proxy for something else. And usually we're not this lucky that it just kind of goes through immediately. So here's kind of another example where I have a one-dimensional function and 4 cover elements. So here are my cover elements. This is my function. And I want to start bringing in persistence into this, right? So let's look at a specific sublevel set, and kind of an immediate, the first perhaps take on a persistent good cover would be to say that, okay, well, at each level we have a good cover, right? But this ends up being very, very restrictive. So in this example, this cover element for this sublevel set is certainly contractible. So this is okay. And actually, if we would go through all the sublevel sets, this cover element would be just fine. But if we look at the one next to it, well, at this sublevel set, it's no longer contractible. It doesn't have the topology of a point, right? Why? Because it appears as 2 components. So, because this definition is quite restrictive, people have done a lot of work to make it less so. So usually what people do is they say, well, it doesn't always have to be, it doesn't always have to have the topology of a point, but perhaps for every epsilon sublevel set, it should have the topology of a point. So usually, kind of the prototypical case in my mind for how this happens is if I have a very small cover elements and a Lipschitz function, well, as soon as a cover element becomes non-empty, soon after it does have the topology of a point, simply because it's very, very small. The downside of this approach, of course, is that I require a very fine cover, and this has negative consequences if I when I actually do computation, because I will have a lot of simplices in the nerve. So, we want something that's even less restrictive than every epsilon having a good cover. So let's kind of take a look at what our input is and what we actually want. So we start off with some function on a space and a cover. So we consider this as the input. Now, what we have on the left-hand side here is a diagram, let's say of the sublevel set persistence. It's not particularly important what we take. And on the right-hand side is what we actually compute, right? So on the left-hand side, this is what we want. This is what we can compute. We take our cover, we construct the nerve, we build a function on the nerve. I'm not going to I'm not going to define this precisely. There's one kind of natural choice of this, and with a little bit of thought, I think everyone can kind of figure it out very quickly. And then the diagram of this function on the nerve is what we can actually compute. And what we're after is some kind of approximation result between the two, right? So in the case of the Nerve theorem, let's say that we have a check filtration where at each level of the filtration, we actually have an isomorphism between a cover and the nerve, right? The same homotopy type. Then, then this is very clear on what kind of information we have, right? But again, we don't want this to be really an isomorphism. We don't want this to be an equivalence. We want it to be an approximation. So, the question now is... And
Primoz, just to interrupt really quick, simple question, but on your right-hand side, you have the diagram of the nerve, comma, G. That's just a filtered simplicial complex.
Yes.
Right.
Yeah. So think of the same way of a sublevel set filtration of F. If I build G, I can do the sublevel set filtration on the nerve, right? So it becomes a filtered nerve.
Thanks.
Okay, so the question now, of course, is, what is the right definition of an approximately good cover? So there's a lot of different ways to do it, but I think perhaps one of the more natural ways is first, what do we do generally in persistence when we want to replace isomorphism with an approximation, well, we talk about an interleaving, right? So here, I'm not going to go through interleaving since I think it's well known enough now, but the point I want to make here is really that it's what we think of as the standard measure for proximity for persistence modules. And the whole point here, the only thing I really want to point out is that I'm going to be using this notation, which is perhaps a bit non-standard, to say that F and G as persistence modules are epsilon interleaved, right? And epsilon interleaved means here that I can go forward by epsilon and then back, right? So this is really kind of the point, all that I really want to say here in terms of defining interleaving. But the important thing to say, well, when we want to talk about approximately good covers is, well, a good cover is somehow homologically trivial or topologically trivial. So the natural notion for, let's say, approximately good covers would be to say that we would need this notion of a trivial module, right? So a trivial module is just one with zero, right? That's the only element in the module. And so an epsilon trivial module is one that is epsilon interleaved with zero, right? So if you prefer to think of this in terms of diagrams, well, a trivial persistence diagram just has the diagonal, whereas an epsilon trivial diagram has no points that are further than 2 epsilon away. So these twos come in at various places. It's not something I'd want to stress during this talk because it gets very confusing. But up to a factor of 2, things should make sense. The other thing I want to say is that I'm not really going to consider diagrams, and I will kind of point out at different points why I'm going to just talk about interleavings rather than kind of the standard bottleneck distance between persistence diagrams at different points during the talk. Okay, so what is our goal, right? So we know what kind of small things should look like, right? We're going to say that these are epsilon trivial things. So we're going to say that given a cover, we should have, so cover with a function, what we want, we're going to call the cover epsilon good if all the little pieces, so each cover element and each finite intersection of the cover elements has a corresponding persistence module that's epsilon interleaved with 0, right? So if you think about just one cover element, it covers a space with a function. So you just consider the restriction of the function to that little cover element, and you compute its persistence module. And if it's epsilon interleaved with 0, then we say that piece is epsilon good. There is an important notion here. Notice I have reduced persistence modules written here. This is to avoid a technicality because we know that any persistence module in dimension 0 is always going to have an infinite component corresponding to the actual component, because even a point has one infinite component. So this reduced is just a mechanism, an algebraic trick to avoid really talking about that, right? So you can think of it as just ignoring that infinite component that's first born. Okay, and what we're going to try to prove is to say that, okay, let's say that each of my finite intersections are epsilon good, then the underlying space, or rather the persistence module arising from the underlying space and the one coming from the filtered nerve are in some sense close, and we're going to try to figure out exactly what close means. Okay, so before we get to kind of how we do this, I want to do a slight interlude in terms of a refinement of interleaving. And the reason is, I think if we think of interleaving in a slightly different way, the proof actually becomes much, much cleaner. So what is this refinement? So Uli Bauer and Mike Lesnick a few years ago now proved in this very nice paper that this single morphism characterization of interleaving, where they said two modules are interleaved if and only if there exists this short exact sequence in this function f where the kernel of this function and the co-kernel of this function are epsilon trivial, right? So they're epsilon interleaved with 0, right? So this is kind of the starting point of where to think about this. We're going to think about it slightly differently in that we're going to define rather specialized types of interleavings. So we call these left and right interleavings. Essentially, we say that a module is M is left interleaved, is epsilon left interleaved with N if there exists a short exact sequence such that the last term, the last non-zero term, is epsilon interleaved with 0. So here I use epsilons for modules that are epsilon interleaved with 0. So clearly this M, the map between M and N has to be an injective map. And the dual of this is where M and N have a surjective map, and the kernel of that map is epsilon interleaved with 0. So we're going to call that a right interleaving.
So, question here.
Yes.
So in the Bauer-Lesnick formulation,
yes,
you had a map from A to B, and it shifted the filtration by epsilon.
Yes. Yeah.
For your maps between M and N,
no, it's there's no shift. They're ungraded. Okay.
Okay.
Okay. So this brings up a few different possibilities if we look at it, right? Because if we think of left and right interleavings, the natural thing we want to do with them is compose them, right? So we can compose M left interleaved with N and N right interleaved with P. And I mean, these are four of the most of the kind of non-obvious compositions. And there's a few things to note, two main things to notice. The first thing is that this left and right interleaving is not symmetric. If M is left interleaved with N, unless it's an isomorphism, generically its N is not left interleaved with M or even right interleaved, and kind of vice versa. And the reason we actually came up with this, and it's going to become kind of obvious when we get into the proof, is they can't interact in the following sense, right? If I think of any one of these lines, right, these are two short exact sequences, and I want to relate M and P. If I have these two sequences, essentially what we can prove is that M is epsilon interleaved with P. Here, in this case, M is interleaved with P. I mean, in each case, actually, M is interleaved with P. And it's quite interesting. I'm not going to go through the proof here. It's mostly diagram chasing. You write down some diagrams and you show that they commute. So these first three compositions are actually true for very general modules. We don't really even need, I mean, in none of these things do we actually need a persistence diagram to exist, but this would hold even if it's kind of, homology over some more complicated ring. Whereas this last case, and I don't really know why, but this is only true for one-dimensional persistence modules. And kind of more specifically, we use the fact that these one-dimensional modules have a projective dimension of 1. So I'm not sure whether this is just an artifact of our proof technique or whether there's really an obstruction to this kind of composition for more general modules. And that's kind of an open, yeah?
By one-dimensional persistence module, you mean exactly what you said. It has projective dimension 1. You don't mean it's not one-dimensional homology. It's nothing to do with that dimension.
Yeah. I mean, this is 1D as in the parameter, right? So versus multi-parameter persistence.
Okay. Got it.
Yeah.
Thanks.
Okay. So the reason we started looking at this is going to become obvious in the proof, but there's kind of an interesting consequence I would mention as an indication that there's something deeper going on here. And we were able to prove, actually this should say theorem, is that if I have an interleaving, or rather it's a different characterization of interleaving if and only if there exist three modules into basically decomposing them into right and left interleaving. So one direction follows directly from Bauer and Lesnick. The other direction basically requires this type of diagram and arguing on it. the reason I think this is also interesting is that at least morally, what these left and right interleavings are doing, you can think of them as shortening and lengthening bars. And although it's not a precise analogy, in principle, when we compare diagrams in terms of bottleneck matching, we usually think of, well, you know, I'm going to shorten some bar and I'm going to lengthen some other bar, and I'm going to match the bars that way. But we have some conjectures in the paper, and you know, I still think it would be good to understand, you know, exactly what the relationship of these right and left interleavings are to lengthening and shortening bars. And I think this would be especially useful for understanding stability of more complicated cases like multi-parameter persistence. Okay, but that's kind of a separate story, and you know, there are mainly open questions there. Getting back to kind of the Nerve theorem, right? We're now going to be able to actually construct how close the persistence module of the filtered nerve and the actual underlying space are. And rather than kind of give a lot of definitions, I want to give an example. So I'm going to restrict myself to a very simple case here, which is going to be a cover of a complex by subcomplexes. So every cover element is a complex, every intersection is a complex, every three-way intersection is a complex, and so forth. One can set up this machinery more generally, but it gets much more technical. So here I have three cover elements of a simplicial complex, and actually this is a good cover. So if I think about each piece, it's actually contractible, and if I take the nerve, I see that I get a cycle here that exists here, and there's nothing else, right? So actually, if I look at the homology, I have H01 and H1 of rank 1, and it's the same as my underlying space. The nice thing about the approach I'm about to show is that the function doesn't ever really come into it explicitly. Everything I'm going to say, or almost everything I'm going to say, holds whether you have an unfiltered complex or a filtered complex. And I'll point out where the details are. Right? So what we want to build is this construction called a double complex. So it's basically just a way of organizing information. Here, there's three indices that are important. I want you to ignore the top right one for now, but we're just going to define E0PQ as Q chains in the pth order intersection. And if that doesn't make any sense here, let me show you in this previous example. So up here we have the same example as before. And what we do is, for example, for 0, 0, we take all the vertices in all of the cover elements, in the single cover elements, right? So here I have all copies of everything that's in A. Here I have everything that's in, here's everything in B, and here's everything in C, right? So it's A, B, C. Here are all the edges that are in A, here are all the edges that are in C, and here are all the edges that are in B. And then the second column is basically everything that's in the pairwise intersections, right? So there's two vertices H and D in the pairwise intersection and one edge between them. And of course, the three-way intersection is in this case empty, right? But this is kind of the construction, the setup of the double complex. Now, the important thing to notice is that things appear multiple times, right? So, for example, anything that's in a pairwise intersection is going to appear twice, right? If I had something in here in the three-way intersection, it would actually appear 3 times in here, right? So this is just kind of the construction. This is really a definition rather than anything else. Right now, it's not yet a complex, but we do have some chain maps between these things that we've defined. Here I call them, boundary 1, boundary prime, and boundary prime prime, to kind of get an idea of what these maps are. The vertical maps, so boundary prime, is basically just the sum of the individual boundary operators, right? So this triangle maps to here, to this cycle, and then this cycle maps to these three vertices here, right? And so for each piece, you can take the boundary operator and then you just take the direct sum together. And here, the same thing for the pairwise intersection, right? You take each piece and it's a complex, so it has a boundary operator. So the vertical map is actually quite natural to and easy to understand. The horizontal map is just the identification of each piece to where it occurs, right? So for example, this H will map to this H and this H, right? So it's still a chain map, right? And actually it maps to the sum of these two. So the important thing here is that it's still a chain map. And we're not going to do it here because it's quite tedious. But over the formula I have here is over Z2. But the point is that if you consider these kinds of squares, right? So this actually defines a boundary operator. And the boundary operator is not on single squares, but rather over anti-diagonals. So you take each anti-diagonal, apply this boundary operator, and it maps to one anti-diagonal lower. And it turns out this is a real complex. So this is called the double complex. Sometimes it's also called the total complex. And there's a very general result that says that the homology of the total complex is the same as the homology of the space. So if we were to compute the homology with respect to this boundary operator, persistent or otherwise, we would get exactly the right answer. Okay, so what have we actually done here? Well, now we're going to actually apply a spectral sequence.
Pretty much one question, just to interrupt you. So the vertical boundary operators, when you compose those twice, you get 0. Yes. And same for the horizontal ones.
Yes.
Okay, thanks.
Yeah. So, okay. So we're going to apply spectral sequence. Why do we need some other tool? Well, all we've really done is expand the amount of information we actually need to keep track of. So our problem is in some sense more complicated than what we started with. So I will say that a similar Don Sheehy and his student looked at the same problem, and they actually have a way of dealing directly with this double complex and building chain interleavings. The result ends up being the same, but the technique is kind of completely different. The technique we're going to be used is a spectral sequence, right? So spectral sequence is one of these things that tends to scare a lot of people, but for the purposes of this talk, we're just going to think of it as an iterative algorithm. So each step of the algorithm is called a page, and we're just going to run through the algorithm. And so our input is this double complex, and when we finish, what we hope is that we get the homology. It's not going to be quite the right homology, but we'll be able to fix it in the end. So okay, let's see how the spectral sequence runs. So first, we're going to take the vertical maps, right? So just each individual piece and compute the homology of this, right? So we've started with chains, and this way we go from E0 to E1, and each E1 PQ is basically just the direct sum of the qth homology of the pth intersections, right? So if I think about the nerve and all the chains that kind of map into that simplex in the nerve, then what I'm doing is I'm taking that piece and just taking the homology, persistent or otherwise, and that's my E1 page, okay? So this is very easy to understand. It's just the direct sum of a bunch of homologies. Then of course this isn't going to be the right answer, so we need to go to the second page. So these maps are already a little harder to understand, especially if one wants to argue about them, but it's quite easy to see that they're well defined. Recall that deep partial prime prime was a chain map, so it automatically induces a linear map, or rather it induces a map on homology, right? So these E1s are just homologies, and so D1 is just the induced map from that chain map that was given. one needs to check that the induced map still is still a boundary operator, but it turns out that it is actually the case. So we do the exact same computation before, which is homology. We take the kernel mod the image, right? So for something like this, we take the kernel with respect to this map and mod out by the image of this map. So it's a computation that we know how to do, and so we do it and we get E2. Right? So the higher differentials we still not necessarily done, and this is where things can get really confusing. So E3 is there's gonna be with respect to D2, which look like these, right? This map. And there's actually a general formula for how these things go. And if these indices don't necessarily make much sense, especially I'm sure if you haven't seen it before, looking at kind of the pattern, I think will help shed some light on the situation. So here I've written, here I have E0 with D0, E1 with D1, E2 with D2, and E3, E3 with D3. And you can see kind of the pattern that's emerging. And this is exactly what's encoded in these coefficients. If I look at D2 and I want D3, well, I just go one up and one to the left from the previous one. So D4 would, from here, would go one up and one to the left. So it would go somewhere out here, right? And I know that when people first see this, it seems very mysterious. So I thought I would kind of very briefly go through the construction of these differentials. In spectral sequences, generally, we don't have access to the higher differentials, but in this case, since we actually have all the information, we can explicitly construct them. And it's very similar in spirit to how one does the connecting homomorphism for, let's say, a short exact sequence to a long exact sequence. So here I have the E3 page, and I'm going to take an element in this part, right? In this part of the third page. There's some homology class. I'm going to take a chain representative, and I'm going to apply D2 to it, right? So recall that E3 is essentially kernel mod image of D2, right? So I can apply this chain to here. And because it's in the kernel of this map, I know that it maps to 0. Now, it only maps to 0 in homology. It might map to something, to a cycle at the chain level. But let's say that it does. Well, because it maps to 0 in homology, I know that it has to be a bounded cycle. So I can pull this up, one dimension up, and then apply my chain map here, right? This boundary prime, and I hit something. And if I hit another homology class, I define D3 as mapping this class to this class. This is kind of just really a rough idea. To kind of get a better feel for this, one really needs to write out the equations. But this is the general idea behind the construction of these differentials. One of the benefits of what we're going to do, though, is that we're not really going to need to know these differentials very precisely. Okay, so when can we actually stop, right? When does this spectral sequence finish? Well, again, I have the D3 page here, and let's say that these are all the elements that are non-zero. So everything above is 0, everything to the right is 0, and actually everything to the left and below is 0 as well. So now when I go D4, when I want to compute D4, well, again, I go one up and one to the left. So everything actually in here is going to map into 0, and everything that's going to map into here is also going to be 0. So if I want to compute the next page, essentially I'm taking the kernel of something into 0, mod the image of something 0 into something. So that's actually just the same thing, right? So no matter, after this point, no matter how many times I take the differential, I'm going to get the same thing. And so at this point, I just say, okay, the spectral sequence has collapsed, and I call this the E infinity page. Okay, so now let's take this machinery and try to prove the homological nerve theorem. So just a very simple case where we have a good cover. And let's look at the E1 page. Now remember, the E1 page is just the homology of these little pieces. So it can't have any higher homology, right? Because it has the homology of a point. So everything up here is 0, and then there's some things here, right? And so we still need to take the first differential, which is this induced map. But everything is concentrated down here. So it turns out that because everything's concentrated down here, E2 is essentially where things collapse, right? Because any D2, everything afterwards is just going to map up, and from below it's going to, again, map from 0 to something, so we're finished. So we are at E infinity, actually. And it turns out that once we're at the E2 page, in this very specific case, we can actually just read off the k-dimensional homology as the direct sum of the antidiagonals. And specifically because everything on the antidiagonal except the first element is 0, right? This just reduces to whatever element is in this position. And one can show that this is exactly just the homology of the nerve, right? Because this induced map is actually exactly the same thing as the differential of the nerve. But this is a good cover, right? So now we want to kind of extend this to an approximate good cover, right? So let's look at what this assumption means again on the E1 page, because it makes sense to think of it in terms of homology. So instead of zeros, essentially, I'm just going to replace things that are epsilon trivial, right? So rather than 0, I'm just going to put epsilons here, and this is really the homology. This is really the underlying space, right? So this is a real underlying space with the real function, with the given cover the double complex has this property, right? And so if I'm also going to look at the E1 page of the nerve, which the nerve, remember, kind of assumes that it's a good cover, so we can kind of put zeros here. And each of these pieces is epsilon interleaved, right? So these are kind of trivially epsilon interleaved, but these are kind of epsilon interleaved by assumption. Okay, so going from the E1 to E2 page kind of requires explicit computation, and I didn't want to kind of do that, so I'm just going to kind of say that you lose an epsilon factor going from E1 to E2. But again, the map there is quite clear, so it's very easy to kind of prove this result. But now we're at the E2 page, and again, we're going to say that this thing is 2 epsilon interleaved with this is 2 epsilon interleaved with this, and so forth. So what we're going to first notice is on the right here, this is exactly the homology of the nerve, right? So this is the 2 homology of the nerve, the 2-dimensional homology of the nerve. This is the 3rd dimension, H3 of the nerve, and so forth. And we know that, so this is the way we're going to go. We're going to relate the nerve to elements here, right? So everything, again, we're going to concentrate on this first row here. And so we know that each one of these is exactly the same as the homology of the nerve. And then this F is 2 epsilon interleaved with this corresponding E. Okay. So, for the nerve, we're actually done. But now we're going to run the spectral sequence on the real space and see how bad it can actually get. So here, right, everything on top for all pages is actually always going to be epsilon interleaved with 0, because in some sense, you're always computing submodules, and the way to think about it is that noise can't really grow, right? So, it may become smaller, but epsilon trivial remains a valid bound for everything above here, right, for all pages. But what we care about is this first row, and that's a little more complicated. We need this, we need to compute the full formula, but actually we can even simplify it. So first thing to note is because it's on the first row, everything comes up from below it. So we can ignore the image, right, because it's mapping from 0 into it. So we can completely ignore this quotient. So we get this kernel, and it's always going to map up into this pink part, or 0. So we can just look at the kernel of something into an epsilon trivial module, right? And if we write this down, well, what we get is a short exact sequence of an epsilon left interleaving, right? So this kind of very explicitly gives you an epsilon left interleaving between the n+1 page and the n page. Okay, so now I can just put this together. I can say, okay, well, how many steps do I need to do this? I'm going to call that D. And I'm going to say that, okay, E2 and E infinity are 2D minus 1 epsilon interleaved, right? Because I need to do D minus 1 steps from E2. Because I'm essentially starting at E2, I need D minus 1 steps. And the interesting thing here is that D is the minimum of the dimension of the space and the nerve. So even if one of these is infinite dimensional, the result still holds because the spectral sequence will eventually collapse, right? So this is really just kind of any way that you can bound the number of non-trivial differentials will give you a valid bound for this D, right? So it's because it's just the number of steps I need to do. Okay, so if we were in a really nice situation, we'd be done now, right? Because I said, I had it written that, E infinity is what we want out, but unfortunately we're not quite done. So there's one more step. We need to relate the E infinity page back to the homology of the space. So even though what I'd written before is that it's the direct sum of these anti-diagonals, it's unfortunately not true. It's only true if the modules are freely generated. Now, in the case of a good cover, because everything was 0, extension problems are kind of trivial. Whereas in general, because we have epsilons here, we can't really ignore the extension problem. And I want to highlight what this extension problem looks like for the case of persistence diagrams, because I think it's quite handy to see it, an example of it. So rather than the full spectral sequence, I'm just going to consider the Mayer-Vietoris long exact sequence, right? So I just have 2 cover elements. The nerve can't really have any homology, can't have anything interesting, but each individual piece can have it. And here I want to consider the persistent case. So I have this cycle here, and then part of it gets filled in, and then the other part gets filled in, right? So it's discrete time steps, and but no one cover element at the beginning. It's spread out across both cover elements at the beginning, then it gets kind of localized to here, and then it dies, right? So this is going to be our example. And okay, let's take a look at what it looks like. So the intersection looks like 2 pieces that get connected and then stay connected. The direct sum, right? So each individual piece looks like first just a piece, and then this piece closes up, and this piece closes up as well, but gets filled in immediately, and then the other one gets filled in as well. Whereas if we look at the union, we have this cycle, right, that's born here, and then persists all the way to here, right? So let's look at the actual barcode for this, because I think it helps, right? So here I have dimension 0. There's nothing in dimension 1 in the intersection. I have 2 components, and basically this one component dies here. And here I have a one-dimensional cycle that lives from time 1 to time 2, essentially. The other cover element doesn't have any interesting homology, really, just this one thing that is born and dies immediately. But the union has a one-dimensional class that lives from time 0 all the way to time 2. So what's going on here? I haven't seen anything in the intersection or any one individual piece that spans both time steps, right? Especially in dimension 1. Well, what happens is these 2 essentially link up to form this one. And that's exactly the extension problem. Point-wise, if we think of the rank of the homology group, everything is still exact, but the way these things map together may not be trivial, right? So kind of going back to the spectral sequence, I kind of abused notation here and said that, it's true point-wise, which means that if I take any one time slice in my filtration, this direct sum is true, but the way things kind of link up, right, the maps between them might not be the same, right? And so, each of these problems is essentially bounded as an extension problem along each anti-diagonal. So, we had to prove a lemma that says that if it's an epsilon good cover, then the E infinity page and the underlying space are again 2D plus 1 epsilon interleaved. So where does this D plus 1 come from? Well, D plus 1 is the length of the longest anti-diagonal, right? That's quite simple to show. But now I do want to say maybe just a few words on what is this extension problem. So for people that know spectral sequences, they know that the E infinity page forms another filtration. If that doesn't make any sense to you, don't worry about it. All you need to know is that there exists this short exact sequence. And essentially what we're going to do is we're going to start down here and we're going to try to kind of incorporate the information from one step up to get a new extension, and then kind of do this repeatedly until we get up here, and then we know we have the right answer. So I don't want to get into the notation too deeply, but the way to think about it is that this is something up here, right? And this is my current approximation, and the problem is finding the module inside here such that this will be exact, right? And the way one would do this is at the chain level, right? If one actually wanted to compute this, you have to lift up to the chain level and to kind of disambiguate what is the module structure here in the middle. Okay, but here we get our extension. Now, the important thing here is that everything along the anti-diagonal except the first thing we can replace with epsilon, right? Some epsilon trivial module. Now we have a short exact sequence that looks something like 0 into epsilon into something, right? So this is exactly an epsilon right interleaving between the extension and the current approximation, right? So it doesn't necessarily mean it needs to be this bad, but it certainly bounds how bad it can be, right? And the benefit of this approach is that we don't really need to know any of the details of the maps, right? We just know that it's an epsilon right interleaving kind of by definition. Okay, so now we're basically done, right? So essentially what we did was we related the Pth homology of the nerve with this E2 term. We relate the E2 term with the E infinity page. That's essentially the spectral sequence. And then this extension problem goes all the way to the space. So if we just apply triangle inequality, we get this factor of 4D plus 2 epsilon. However, if you recall, this step here was a left interleaving and this is a right interleaving. And we know that they can't interact. So we can just take the maximum of the two and we end up with this 2D plus 1 epsilon 2D plus 1 epsilon factor, which is actually the right answer. And that's actually kind of one of the main theorems in the paper. So kind of concluding, that was the result. I didn't have time to kind of show the counter example, or rather the lower bound example. I gave you a hint of it in that Mayer-Vietoris example. That's kind of the two-dimensional example, and one can generalize it to show that this 2D plus 1 epsilon is actually tight.
Primoz, that was the example sort of with the figure 8, or you had the two.
Yeah, exactly. Yeah, right. Yeah. So where I showed the linking, right? So the linking is essentially one way in which you can kind of achieve the bound. In the paper, there's bounds for all the different steps. One can construct various things where things go wrong. So one thing I want to kind of say is that the really starting point of the analysis is this double complex. And double complexes don't just appear in this case, but kind of much more generally, right? So I think without too much work, certainly this looser bound of 4D plus 2 would certainly hold for kind of multi-parameter persistence or multi-dimensional, depending on which name you prefer, or even at the level of something like homology over Z, which over the integers, where a diagram might not exist or doesn't exist necessarily, but as modules you can still talk about the interleaving. So one thing that I think I've been thinking about is what other interesting cases of double complexes can we come up with where the same kind of approximation approach would tell us something. Another thing that I kind of want to mention is that, one of the original motivations I had was to consider this situation where I have a very big complex and I cover it with kind of coarse cover elements, and I can't compute the entire persistence, but I compute the persistence of the nerve. If each of these pieces is kind of small enough that I can compute on, I can actually obtain error bounds, right? So I don't want to run the full spectral sequence, but I can kind of simulate it and obtain kind of an outer approximation of how much I've lost by switching to this cover, right? And I don't know on how to use this, but in principle, one could think of using this to kind of adaptively build a cover of a really big complex so that, so to make kind of let's say, an error-aware cover so that we lose as little information as possible while, making things as computable as possible. So two other directions that I kind of want to mention is, here we used kind of very specific epsilon interleavings, how one would do something like this for Wasserstein distances, which, there's no interleavings defined for Wasserstein or even more general interleavings than that. This is kind of current work. And, I do think that this nicely kind of packages a bunch of results that are out there and can be useful, right? And I think the whole left and right interleaving as short exact sequences is kind of I do think that there's still something there, and there's still quite a few things that aren't completely obvious from this kind of perspective. So I think with that I will finish, and and if there are any questions, I will gladly answer them.
Thanks so much, Primoz, for the very nice talk. So if you're quick enough on the trigger, go ahead and unmute yourself, and let's thank Primoz. And then questions for our speaker. So I have a question. Your bounds depend on D,
yes.
And in your results are much more general than the very first example you gave of making a very small cover where you have sort of these Lipschitz functions and sort of the
Sure.
errors. But in spirit, is these bounds depending on D? Is it similar to those that Lipschitz constant example?
So no, because D doesn't necessarily depend on anything with the Lipschitz constant, right?
But D sort of okay, I guess D what does D depend on?
I mean, D depends on your underlying space and the dimension of the nerve, right? So if one is lower than the other, you take the minimum of the two. But there's something I didn't quite mention, which is, in principle, the approximation factor depends on how many steps you need to do, right? So if I care about, let's say, k-dimensional homology, I could just as well replace I could replace D with K, right? Because if I don't care about the higher dimensional things, I can just go up to K and, everything is fine.
Right, because you don't need to compute any further. Okay. I see. So for one-dimensional homology, you can say take D to be approximately 1.
Yeah, exactly. Right.
Right.
Yeah. And I mean, kind of trivially, right, the zero-dimensional case is kind of even easier.
Mm-hmm.
Yeah. And since I guess that's actually an important point, since most of the time we only really care about to dimension 2 or 3, right? We don't usually compute much higher homologies than that.
So another question that I have, I'm interested in things like you take the 2-sphere and you take all geodesic balls on the 2-sphere, and for a while the balls are small enough such that the Nerve Theorem applies, but eventually the balls intersect as a circle, and the nerve lemma no longer applies. So the 2-sphere is sort of unknown what all these nerve complexes arc. But the circle it's known. So in the circle you have these arcs, and then once the arcs collide, you get the three sphere, and then so that's when the arcs go halfway around the circle. And then when the arcs go 2/3 of the way around the circle, you get these threefold intersections that are three disconnected pieces, and you get the five sphere, and it sort of keeps going like that. So, I mean, so this is these are infinite simplicial complexes, but let's, we could discretize them. So take, evenly spaced points around the circle and then grow these arcs. I'm trying to think what your results
So
give
there
here.
is an implicit assumption here in epsilon trivial, right? In that, in the end, it has to be a good cover, because otherwise it can't be epsilon trivial. It's kind of a simple consequence if you think about it for a little bit. But in principle, what I'll say is that you won't get an exact kind of an immediate approximation result, but the spectral sequence will still hold, right? The only point is that now when you have when things start intersecting, in different ways, you start getting things higher up that are non-trivial at different points. And you can still use the whole paradigm of the spectral sequence to kind of track and try to understand what goes on, right? So you could still get, for example, bounds on when things are born and when things are born and how things kind of link up in certain ways. I think you could still use the spectral sequence for that. It's just not going to have this very simple form of these epsilon trivial modules, right?
So is it the case that we still have epsilon trivial modules? You just have to take epsilon to be pretty large, just because.
Well, I guess I guess everything's an epsilon trivial module in some sense, if epsilon is big enough. I don't know. I suspect that the bounds you get would not be terribly useful. And again, this spectral sequence is in some sense straightforward enough that I think you can look at these maps kind of more directly and not depend on the epsilon triviality, but kind of, use the fact that basically run the spectral sequence directly and then look at the extension problem directly to kind of try to understand what happens in dimension k, right?
I see what you're saying. Yeah, I agree with you. In that example, epsilon's too big to be useful, but you could still try to run the spectral sequence.
But you could think of, for example, when something wraps all the way around, right? That each cover element is going to have, might have, depending on the shape of, for a sphere, right? For a sphere, actually, right, once it wraps all the way around, you're just gonna have whatever number of copies of the sphere, right? And so that's going to tell you something about the topology after that point, right? You can kind of, if you can track kind of individual pieces, even on the E1 page, that's going to tell you where things can actually happen, rather than, it's going to lower it's going to kind of reduce the number of things that can actually happen very, very quickly. So I think there would be a lot of kind of important information there. It's just not going to be quite as easy.
Right. Other questions for Primoz?
Hello. My name is Luis. I didn't get the reduction of the dimension in the last page.
Which one? This?
Oh, the last. Yeah. This. How do you end up with? Sorry. I just figured out that you factor the two. Sorry.
Yes. Yeah. Okay.
But how do you say that the result in dimension one applies to that?
Oh, so if you think about the step from going, if I have, so the step here, right, between E2 and E infinity, if I just fix P, is actually limited by P steps, and the extension problem between EP0 and HP is again limited by P steps. So you can just replace this D here. If I don't consider all the dimensional homology, but just the p-dimensional homology, I can replace this D here with this P up here, right?
Right.
Because,
yeah. Thank you.
Because it's just the number of steps I need to do in order to converge.
Yeah. Thank you.
Other questions? Let's thank Primoz again.